Building transportation infrastructure in today's evolving world requires construction techniques that meet stringent standards for safety and long-term viability. New techniques can offer better solutions, but at the same time must remain competitive both in cost and in construction time. Geopier Foundation Company has been at the forefront of new technology relating specifically to soil reinforcement for support of transportation structures and embankments. In recent years, Geopier technology has proven to be a superior alternative to deep foundations or traditional ground improvement methods in many transportation-related applications. First, let's look at Geopier soil reinforcing elements as an effective solution for supporting heavy highway and railroad embankments built on weak or compressible foundation soils. When existing soils needed to support embankments are exceptionally weak or compressible, the heavy loads from the weight of the embankments and live traffic loadings can cause overall settlements as great as several feet or more. Global instability in weak soils is another concern. Excessive shear forces can cause a bearing capacity shear failure. In the past, soil has been stabilized through the technique of over-excavation and replacement, requiring the removal of poor or weak soils and replacing it with stronger materials. The disadvantages associated with the over-excavation method are well documented. These include high cost, the need for massive amounts of select materials, slow construction schedule, unstable bottom conditions caused by high groundwater, and construction delays from inclement weather. As an alternative, Geopier soil reinforcement is a refinement and improvement to the over-excavation and replacement method. The process of constructing a Geopier element first involves drilling or excavating a cavity. Depending on the specific design requirements, drill depths normally range from 3 meters to 8 meters, or about 10 to 26 feet. Once the cavity is completed, a small volume of clean stone is placed into the bottom of the cavity. A special tamper is then activated on the surface of the clean stone. The tamper uses impact ramming energy to pre-stress and pre-strain the soil at the bottom of the cavity while making a bottom bulb. Open-graded or highway base course stone is then introduced into the shaft of the cavity in thin lifts of 1 foot thickness. The tamping system again uses impact ramming energy to compact the aggregate. A specially designed beveled tamper pushes the stone laterally against the soil, increasing the lateral stresses in the adjacent soils and thereby strengthening the Geopier element being installed. When supporting highway and railroad embankments, Geopier elements reduce settlement because of the high stiffness of the piers that attract a disproportionate amount of the applied stress, significantly reducing the vertical stress applied to the compressible foundation soils. Additionally, the matrix soils are made less compressible because of lateral stress buildup. When Geopier soil reinforcing elements are constructed out of open-graded stone, they act as vertical aggregate drains, allowing for faster consolidation of the compressible foundation soils. This significantly reduces the time required to achieve total settlement. A recent innovation that has proven effective is to support heavy embankments with a structural geogrid system, such as a Tensar geogrid load transfer platform supported by Geopier elements. In addition, friction angles on the order of 50 degrees have been measured for Geopier elements in both full-scale field shear tests and laboratory tests. The high friction angle provides a significant increase in shear resistance and prevents global instabilities resulting from below-ground bearing capacity shear failures. A specialized use of Geopier soil reinforcement that has proven highly effective is in eliminating the bump in the road at the end of a bridge, because constructed embankments settle more than pile-supported bridge abutments. Geopier elements are installed within the underlying foundation soils, and at times within the completed embankments to prevent the creation of such bumps in the road. Positive results have been demonstrated by survey and by proof driving the Geopier reinforced abutment approach areas. Another practical use for Geopier soil reinforcement is to support retaining walls that hold back highway and railroad embankments. One beneficial characteristic of Geopier elements is their unusually high uplift resistance capacity. Typical design capacities of uplift piers, depending on length of pier and soil conditions, range from about 20 tons to 40 tons per single pier. When retaining walls need both compression resistance elements to control settlements and uplift resistance elements to control overturning, Geopier reinforcement efficiently provides both. A frequently used embankment retaining wall today is the MSE, Mechanically Stabilized Earth Retaining Wall System, such as Tensar Structural Geogrid. Geopier soil reinforcement has proven to be a cost-effective solution to support these walls. Geopier soil reinforcement has been highly successful in stabilizing active landslides. Roadways built on steep cut-and-fill slopes occasionally result in slope failures, which prevent the roadway from being paved or used for reliable transportation. The high friction angle of the Geopier elements of at least 50 degrees provides an effective remedial method to stabilize failing slopes. Safety factors can be economically achieved with Geopier soil reinforcement that lead to permanent solutions for failing slope conditions. Geopier soil reinforcement is also used to control settlements below box culverts. Concrete box culverts are increasingly replacing bridges. The culverts are installed below existing or new bridges and leveled to allow for flow from streams and water runoff. New fill soil is placed over a culvert to bring the grade up to the roadway elevation, thereby eliminating the need for bridge support. The construction of the culverts and weight of overlying fill soils cause consolidation of the underlying soils. Excessive differential settlements cause damage to the culverts and problems with an overlying roadway pavement system. The Geopier soil reinforcement method controls settlements and prevents box culvert and overlying roadway differential settlement problems. In addition to the positive results it offers, the Geopier solution reduces costs and construction time. When earthquakes occur, seismic shearing stresses propagate from deep rock layers up through the soil profile to shake structures at the ground surface. Shaking within loose and saturated granular soils can lead to soil liquefaction and complete loss of soil shearing strength as a result of pore water pressure buildup. Geopier soil reinforcing elements reduce the potential for soil liquefaction in 4 ways. First, the elements constructed of densely compacted aggregate are not subject to liquefaction. Second, the increase in lateral stress around the piers reduces the potential for liquefaction in the surrounding soils. Third, when constructed of open-graded stone, the piers act as a drain for the dissipation of excess pore water pressures. And fourth, because the elements are stiffer than the surrounding soil, the elements attract the applied earthquake shear stresses, thus reducing the shear stresses applied to the matrix soil. The overall effect is that the Geopier solution changes the behavior of the matrix soil from liquefiable to non-liquefiable. Geopier soil reinforcement is not always the best solution for all transportation system support needs. However, when weak or compressible soils exist below embankments, retaining walls, box culverts, or other transportation structures, and also when liquefiable soils exist, then Geopier soil reinforcement should be considered as a potentially better and more cost-effective solution. Here are some of the many transportation projects successfully supported by Geopier soil reinforcement systems.